So 6.1. Say I talk to 35 randomly selected students at Portales High School and I ask them whether or not they like the cafeteria food. And will my results be the exact same as if I took a census and asked every single student on campus? And you're probably saying no, they wouldn't be. They'd be a little bit different. Well, what if I sampled another 35 students, and it could be some of the same students or it could be different because I'm doing a random sample, so we don't know for sure who we're going to get. But if I do another sample, do you expect those results to come out the exact same as my first sample? And if you're saying no, again, you're right, they're probably not going to be exactly the same, but we'd expect them in the same area. Right. Now in chapter 6 we're going to talk about sampling distributions and the idea that if you take one sample, your results probably aren't going to match exactly with your population or your census results, but if you take many samples, you're expecting them to get really close to what the population would say. So in the real world, we typically don't collect information from the entire population because remember that costs a lot of money, it takes a lot of time, and we don't always get every single person contacted anyway. So if we have to have the entire population if we want to find the mean and the standard deviation for the population, but generally what we do is take an estimate. So with our samples, and when we use these estimates, say X bar and S, to estimate our mu and our sigma, then we're going to have error. That it happens, you can't avoid it, but a big part of statistics is analyzing the errors that you have inherent in your design so that you can make conclusions based on how certain you are that your statistics are close to what the population would say. And that's the whole point of statistics, is to be the science of looking at how can we determine if we're very close to the accurate results or if we're a long ways off and we shouldn't use those results at all. Okay, so we're going to look at some sampling error and statistics for estimating our population values. So remember parameter. That's a numerical measure of a population. So parameter, population, those go together. And it's based on observations for the whole population. And we almost never know what those values really are. A sample statistic, on the other hand, is a numerical measure of a sample. So it's not the whole entire population. So sample statistics, those go together, is calculated from observations in the sample. And those we find. Every day we take samples. Sometimes they're informal samples, sometimes they're random samples, but we're constantly thinking about ask this small group and then make conclusions about the whole population of students, for example, or turtles, or whatever we want to measure. So just to reiterate, we use the sample statistic, and I'll say statistics, to estimate the population parameters. Because we don't generally know the population parameters and we can always find the statistics, we'll use the sample statistics to make estimates of our population parameters. Okay, so we've already talked about X bar and S squared, the variance, and S, the sample standard deviation. We've used those earlier in the course, and we're just going to compare these a little bit and talk about them. This population parameter, here's the variables that we use for them, and I know we talked about them, and I know you guys are really good at remembering which is which, but these are actual values for the whole population, and it's often unknown. And then the sample statistic, these are estimators. estimators for the population values that we don't actually know. So you might have something like all PHS students and 35 randomly selected PHS students. Okay, so remember that wording all goes with population because we're talking about everybody that is of interest to us in a particular question. And then for a sample, we would talk about the smaller group and that we had randomly selected them, because remember, the random selection is what keeps us from having a lot of bias or other error that we don't want in our sample. Okay, and then one more example, we could say all homeowners in the U.S. and then we could say for the sample it would be like, say, 3,000 randomly selected U.S. homeowners. Okay, so here's an example that really gets to the heart of what we're talking about here. Say there's a certain part of Canada where the daily high temperature recorded for all past months of January has a mean of 10 degrees Fahrenheit. So that's the daily high temperature. And so what they're saying is they looked at every month of January since recorded history and they counted up all that data. So that's telling us it's a population figure. And the fact that they used mu is also telling us that. So it's population. And then a standard deviation of sigma equals 5 degrees. So plus or minus 5 degrees for the first standard deviation. Consider an experiment consisting of randomly selected 25 daily high temperatures from the records of the past months of January and calculating the sample mean X bar. So what we're going to do is go back into the records and randomly choose 25 days, that's our sample, 25, and see what the temperatures were for each of those 25 days and then find the mean of those, which would be X bar. Okay? And if we repeated this experiment a very large number of times, like say we did it 25, 30, 40 times, and we refound our X bar every time, we really expect that our X bars are going to be slightly different for every sample because we're looking at 25 temperatures, and when we find the average of those and then another set of 25 temperatures, find the average of those, we don't expect to get the exact same number every time. So for example, the first sample of 25 temperatures might have a mean of 9.8. Maybe the second sample has a mean of 11.4, and maybe the third has a mean of 10.5. So we expect them to be around that 10-degree mean that we found for our population, but they could be above, they could be below, they could be anywhere nearby. And say we did this a whole bunch of times, and then our histogram of the sample means would be approximately the probability distribution of X bar. So the probability distribution of X bar is going to tell us where we expect our mean to show up in all these 25 temperature samples that we're choosing. Okay, and we'll say if X bar is a good estimator of mu, meaning that the mean of all our means is very close to our actual population mean, then we expect the values of X bar to cluster around our mean. And it should look something like this picture here. So we expect our X bars to be somewhere nearby and have most of them around the 10 and then some spread out a little bit from the 10. Okay, so this probability distribution is called a sampling distribution, because it's generated by repeating a sample a very large number of times. So every time we take a sample and we find our X bar from those 25 temperature measurements, we record that, and we do that, I don't know, 50, 100 times, and then we make a distribution of where all our X-bars are, and then we can see this sort of distribution that we see here. So a sampling distribution of a sample statistic is calculated from a sample of n temperature measurements, and it's the probability distribution of the statistic. So that's good news because it's a probability distribution. Then we can say we expect if we make a measurement of our 25 temperatures that the average is going to be within this interval. Remember, that would be 64% or 0.64 probability. So we know a lot about our distribution if it's the probability distribution there. So sampling distribution for X-bar based on a sample of n equals 25 temperature measurements. For example, the probability that you will draw a sample of 25 measurements and obtain a value of X-bar in this interval 9 to 10, and that's just right here, 9 to 10, will be the area under here. And we know that area because that's from our empirical rule. That's going to be 0.34. Okay, so we can use that. We expect the mean temperature or over a very large number of experiments of n equals 25 to be really close to mu. And if we collect our X-bars, our sample means, and make a histogram, we expect it to look like this picture. And now we can use all the things we learned in Chapter 5 about normal distributions to find the probability that a particular experiment's mean, or X-bar, will be in that interval. And we just did a quick example of that. So just a little bit more talking and then we'll get to some problems. Since the properties of statistics are typified by its sampling distribution, it follows that to compare two sample statistics, you compare their sample distributions. So, for example, if you have two statistics, A and B, and you're estimating the same parameter, let's just assume that we're looking at the population variance, and their sampling distributions are shown as we have down here in figure 6.3, you would prefer statistic A over statistic B, and here's why. This one has its center right at our sigma squared, our variance. This one is centered elsewhere. So it's a little bit off from what our actual variance is. So for that reason, we wouldn't like statistic B so much. And then there's one other thing that we look at, and that is the spread. So when we're looking from one end to the other, and we're saying, well, there's less spread here than there is here. So this has small spread, and this one has larger spread. And so if we're trying to estimate our population variance, if we have an estimator that gives us a way wide and kind of flat spread, and its center is off from where the actual variance is, it's not nearly as good as the one that's centered right above our variance and has a fairly narrow spread. So that's kind of an exaggerated example for you of what we're looking at when we try to compare two statistics. So, but then you have to back out again to the real world, and generally when we're doing statistics, we don't know our actual variance and where it is, but we do know that we are going to look sample after sample for the best sample statistic where the spread is less, and then where we hope that our center is in the right position. All right. Now let's take a look at an actual example. And this one is a population information at the top. And so for this population, we know that we have X values that could be 1, 2, 3, 4, and 5. And then we also have the probability for each of those X values. Say it's a 5-sided die or something that there's 5 outcomes, and we want to know what the probabilities are. What we want to do is, if these observations are independent, That's helpful. Verify that the different samples of size 2 and their probabilities are as follows. So we're saying our n equals 2 for this experiment, and we're going to do several experiments, and here's all the possible samples. So we could have a 1 for our first and a 1 for our second, and then we could have a 1 and a 2, a 1 and a 3, etc. So that we're trying to list all of them, and then this one comes back around here and starts over again. So we have actually a double list. It's just shown side by side. And then the probabilities, let's figure out how we got those probabilities. So if we had a 1, 1 for our sample, then we're looking at this one. So we have the probability of 1 is going to be, because they're independent, they told us that, we can take the probability of 1 times the probability of 1, and that would be 0.2 times 0.2, which is going to give us 0.04. And that's what they've got right here. So that's how they came up with that 0.04 for the probability. Because each of those items in the actual population are independent, each of those outcomes, then we can multiply their probabilities together. So that's a helpful thing to see there. So we got the sample values and the probabilities. We've, remember, listed out every single possibility for starting with a 1, and you have 1, 2, 3, 4, 5, and then every single possibility for starting with a 2, every single possibility for 3, for 4, and for 5. And so if we have 1, 2, 3, 4, 5 for each of them, we have quite a few. 5 times 5, so like 25 possibilities there. Okay, then part A says find the sampling distribution of the sample mean x bar. So what I want to know is, what is my x bar? And I'm going to put that right beside, since I have a very nice large table. X bar is the average, so if I have a sample of 2 items and they both had a 1 for the outcome, the average of that is going to be 1 plus 1 divided by 2, which comes to 1. Same thing, or you can think halfway in between your values, so 1 plus 2 divided by 2, so it's going to be 3 halves, or 1.5. 1 plus 3 divided by 2, that's going to be 4 divided by 2, or 2. And you can see we're going up by 0.5, so I'll fill in a couple for us. 3, this is going to be 2 plus 1, or 3, which is divided by 2 is 1.5. And then 2, 2.5, 3, 3.5, and then 3 plus 1 is 4, divided by 2 is 2. 3 plus 2 is 5, divided by 2 will be 2.5. 3 x bar 3.5 and 4. And then 4 plus 1 is 5, divided by 2, 2.5. 3, 3.5. 4, 4.5. 5 plus 1 is 6, divided by 2 is 3. And the last one, 5. So we've got all our probabilities, and then what we need to do now is make a table of our x values, our x bars. So you can see that several of them are repeated, so we're just going to put them in order. Okay, and I kind of want to have a little bit of space. I'm double checking my work on paper to see what I need here. And then I'll want the probability of that x bar as well. So I can see my smallest value, just scanning through, my smallest value is 1, and then I know I was going up 1.5, 2, 2.5, 3, 3.5, 4, 4.5, 5, like that. And I just want to double check that I didn't miss anything. Nope, they're all just going up by 0.5s, and the highest one is 5. And then I want to know for 1, what is the probability that I have a 1 show as the mean? And I know that is going to be 0.04. And since I only have a single one of them, then that's the whole thing, 0.04. And then I'm looking at, I'm just going to put a little check there. And then I'm looking at 1.5, that's my next one. And so I have one that has a probability of 0.06, so I'm just going to write that to the side and put a check by it. And I'm looking for more 1.5s. There's one, and it's also 0.06. And look for another 1.5. And that's it. So the total is going to be 0.12. And I'll just kind of keep those separated so I can see my work. Okay, and then my 2, I have a 0.04. And that's that one. Look down for more 2s. There's one, and it's 0.09. Look down for more 2s. There's one, and it's 0.04. Look down for any more 2s. No more 2s. And then I'll add those up. So 0.17. And then look at 2.5. It has probability of 0.04. 2.5 is 0.06. There's another one. 0.06. Got it. And then 2.5, 0.04. And no more 2.5. So add those up, it looks like a 0.2. And then for the 3, there's a 3, 0.02. And we can continue on this way. Okay. I'm just going to fill in the rest. You can verify that I got them correct. So 0.2 for there, 0.14 for the 3.5, 0.08, 0.04, and 0.01. Okay, so this is my probability of each of those X bars occurring. And then the next step, so that's for part A, that's what we're looking for is the results of part A. And then part B, construct a probability histogram for the sampling distribution of X bar. So I have probabilities, and I know that I'm starting at 1, but I need to go up by 0.5, so 1, 2, 3, 4, 5, and that's as high as I need. 1, 2, 3, 4, 5. And then up the side I can see 0.2 is my highest, so I think I went by 0.02. 2, 4, 6, 8. That's 0.1. 2, 4, 6, 8. And there's my 0.2. Try to make it obvious there. 0.2. And I have 0.02, 0.06, and here I have 0.14. Okay, and now I just want to make a bar centered over each of the numbers that goes up as high as their probability. So for 1, I have a probability of 0.04, so it's going to be centered over the 1. And then for 1.5, I go all the way up to 12, which is going to be here, centered over the 1.5. And for 2, it'll go up to 17, 14, 16, 18, so right about there. And then 2.5 up to 0.2. And it's also the same for 3. So just make a big rectangle there. And then 3.5 is up to 0.14. And then 4, 0.08, that'll be right about there. 4.5, 0.04. And 0.5 is 0.01, so just barely a blip on there. Okay, this is my P of X bar, and these are my x bars. So make sure I label those. And that's my answer for part B. And then what is the probability that x bar is 4.5 or larger? So I can look at my graph, and 4.5 is going to be this block and the final block. So the probability that it's 4.5 or larger, so C, probability that x bar is greater than or equal 4.5. I don't have to use anything except for the numbers I already came up with, and I'll show you why right here. I have the probabilities right here because I came up with the sampling distribution, so I have the actual probabilities. So 4.5 or larger is going to be these final two, and so I know that my probability is 0.04 plus 0.01, which equals 0.05. So the probability that x bar is 4.5 or larger is 0.05. Okay, and then part D, would you expect to observe a value of x bar equal to 4.5 or larger? So do I expect to find values of x bar out there on the end? And since the probability for that end part where I marked it red is 0.05, it's very, very unlikely. So I would not expect to see values of x bar greater than or equal 4.5 because the probability is very small, 0.05. So those values are very unlikely. All right, next question. Refer to exercise 6.5. And we just did that one, thank goodness. And find the expected value of mu. Then use the sampling distribution that we just found to find the expected value of x bar. So expected value, here's my x bar and my p of x. So to find my expected value, remember I have to take the x bar times p of x bar. And so I'm just going to write those out. So 1 times 0.04 is just 0.04. 1.5 times 0.12, you can do that one on your calculator, 0.18. 2 times 0.17, that's going to be 0.34. Yeah, sure, thanks. And then I'll just write the other ones out. And remember, to find the expected value or the mean, you just add up that whole column. And so when I add all those up, I end up with 2.7. So that's my expected value of x bar, or my mean for x bar. Okay, now I also need to find the mean of the x's. So if I go back to the previous page, I had this table, x and p of x. 1, 2, and 0.2, 0.3, 0.2, 0.2, 0.1. And this will be 0.2, this will be 0.6, this will be 0.6, this will be 0.8, and this will be 0.5. Add those up. And this is my expected value of x, or my mean. Okay, so from the population information, my expected value was 2.7 for my mean. And when I did my sampling distribution and then I found the expected value of the x bars, or the sample means, they came out to the same value. And that's what it's saying here. Note that they come out to be the same value.